Hi, today we will see another aircraft instrument. This one is a fuel flow indicator. It is a long instrument, approximately 30 centimeters long. Okay, you can see the part number. I bought this one because it is an instrument from Jaeger, which was a French company. Okay, so it was manufactured in Levallois-Perret, close to Paris. As usual, we will see what is inside. And after I will try to get it work with maybe a reverse engineering. Okay. Oh, beautiful. Okay, so we have first the electromechanical assembly here. Okay, so it is written in French, motor potentiometer. So effectively we have only one device. So this is the servo motor actually. Okay, and we have several electronic boards. So it is interesting because we can remove the boards easily. You can see these connectors here. So we don't need to desolder anything. Okay, so here there are some logic ICs. That code 79 here, 80 for this one. So this one was manufactured at the beginning of the 80s. Logic CMOS. There is an op-amp here. In the middle we have the power supply board. And here we have probably the servo control amplifier for the motor here. We have here 3 modules. And other logic ICs here. There is another board here in the middle. So this one is probably the front-end board. You can see several op-amps. Yeah, so we have a 3 classic LM741. And here there is a 4528, I think it's a monostable. And here there is a toroidal transformer soldered on the power supply board. Okay, so this is the power supply board. 6 AFCO capacitors, 125 degrees. This little board is probably the servo control amplifier. You can see that there are 2 medium power transistors here in TO126, 2 trimmers. On that board there is an op-amp here, LF156, and several logic ICs. We can see other 14528. This is a dual monostable. Okay, and several logic ICs. This is a quad op-amp. Here we have a decimal counter. This is a quad NAND gate. A dual D flip-flop here, 4013. And one LED here for test purpose probably. You can see that we have here 3 electric coding wheels. Probably this hybrid module is intended to drive these 3 coding wheels here. Okay, so this is the torque motor actually. You can see the spring here. There is a micro switch here. It is maybe something optional. Generally, it is possible to have a self-test using a screw here, but you can see that it is not possible to rotate this shaft here. As you can see that we have a little screw here. So I assume that this little screw should push this lever here to activate the macro switch, but the shaft cannot be rotated from the front here. This is weird. And there is a flag here, which is activated by this small solenoid here. You can see the very nice construction using flat flex and this beautiful mechanical die-cast part here. We can see something strange here. You can see that there is a small PCB soldered to the pins of that part 4059. Looks like a configuration board or something, and there is a code on it here. It is time to test this instrument. There are actually two separate inputs. One is an analog input. This is a DC voltage from 0 to 5 volts, which permits to set the analog display here from 0 to 12. The second one is a rectangular signal. The digital display here is proportional to the duration of the high level of the input signal. Okay, so let's turn on the power supply. Currently, the DC voltage is 2.5 volts, which corresponds to the position of the pointer here. And the input frequency is 1.9 Hz approximately, which corresponds to the maximum scale here. Okay, so I am going to multiply by 10 the input frequency. Okay, you can see we have a division by 10 of the result. I will change the input voltage. Zero, okay, and 5 volts. So we can see something interesting when there is a change of the input voltage here. So we can see that there is a change also of the last digit. This permits to indicate that there is an evolution of the fuel flow. We will see on the schematics how this thing is done. I am going to multiply one more time by 10 the input frequency. We should have 0.12. Okay, there is an averaging of 10 measurements here for the digital indication. I did the reverse engineering of this instrument, except the power supply. There are 4 pages. The first page here corresponds to this small board. And this is the input circuit. There is one circuit for the analog display here, and another circuit for the digital display. So let's see the first one. It is very simple. This is the input circuit for the analog input 0 to 5 volts. There is at the input here a sensitivity adjustment, a protective Zener diode here. There is a low pass filter and a voltage follower. The output is fed to the servo control amplifier. The servo amplifier is here. This is the input voltage. And this is the feedback voltage, which comes from the feedback potentiometer here, which is mechanically linked to the needle and the torquer here. There is a differential amplifier here with a gain of 33. One input is connected to the feedback potentiometer, the second one to the input voltage here. So there is also an adjustment of the zero using this trimmer here. This line is connected to a voltage reference. There is another trimmer to adjust the scaling here. The output of the differential amplifier is fed to the final amplifier, which uses this op-amp and this push-pull output here. And the output is fed to the torquer here. This is the input circuit for the digital display. The input is here. The input resistance is 100 kilo ohms. There is, one more time, a protective Zener diode here. The current is limited by this resistor here of 68 kilo ohms. There is a comparator which uses an op-amp 741. There is a hysteresis using this resistor here. This permits to have a clean output signal here. The signal is fed to this bipolar transistor to N2222. This diode prevents a negative voltage based to emitter here. The output is fed to the digital circuits. The output signal here is also fed to this circuit here. This circuit permits to detect if there is a signal at the input or not. The output of the comparator is fed to this retriggerable monostable. The time constant is large here, a few seconds. Therefore, the output here is at high level when there is a signal at the input. This permits also to eliminate this LED here on the board. These two signals are used to clear the counters which are used for the display. This board is a logic board for the digital display. The main circuit is in the center of that page here. The input signal is here. This is rectangular signal or a square wave. The main part is this NAND gate here. There is a reference clock signal at 4.5 kHz approximately. This line is actually a gate signal. At the output here, there is a burst signal. So therefore, the goal is to count these pulses here during the high level. And we can see that there is a divider by 10 at the output of this gate. Actually, there is an averaging of 10 input cycles. We can see that the gate signal is fed to this decimal counter. On Q0 output here, there is a pulse, each 10 input rising edges here. The gate signal is also connected to this monostable, which delivers a positive pulse with a width of approximately 6 microseconds. Therefore, at the output here, there is a pulse like that every 10 input cycles. Okay, so there is a refresh of the display every 10 input cycles here. Okay, so therefore, here at the output of this gate, we have actually 10 burst signals corresponding to 10 input cycles, and the number of pulses here is divided by 10. So here we have an averaging of 10 input cycles. You can see that a measurement is possible if there is a high level on that line. A high level here is provided using a rising edge of the input signal, but we need that the output of the first flip-flop is at high level for that. So we can see that we need a high level first on that line, which is the VCO output, okay, and after that a high level of the input signal. We can see that the measurement rate cannot be faster than the rate of the VCO output. So this signal permits actually to adapt the display rate according to the variation of the fuel flow. Okay, so let's see how this thing is done. The input here is the analog input. On that line, there is a DC voltage which depends on the fuel flow. We can see that this voltage is fed to the circuit, which is a differentiator. Therefore, at the output, there is a positive voltage when there is a decrease of the fuel flow. The voltage is zero when the fuel flow is constant, and the voltage is negative when there is an increase of the fuel flow. Okay, so here there is an absolute value circuit. The voltage here is negative if there is an increase or a decrease of the fuel flow. This voltage is positive when there is an increase of the fuel flow, because in that case this op-amp is in open loop, this diode is off, so therefore there is here a voltage of plus 10 volts approximately. Otherwise the voltage is negative. Okay, so this negative voltage is fed to this low-pass filter, which is also an amplifier. Okay, and this negative voltage here is fed to a VCO, okay, which is this circuit here. We can see that there is a positive feedback with an hysteresis here, and here an RC network. There is a diode here in order to have a rectangular signal, but on that line there is a frequency which depends actually on the rate of change of the fuel flow. Okay, so the frequency is approximately 8 Hz when the fuel flow is constant, and the maximum frequency is 800 Hz when there is a maximum increase or decrease of the fuel flow. Okay, so this occurs when there is a voltage of minus 10 volts here. So we have here a diode which permits to keep only the positive voltage. Okay, when the voltage is negative here, this diode is off and we have 0 volt across this resistor here. The VCO output here is fed to the circuit we just have seen here, this line here. Therefore, the maximum rate of display is obtained when there is a fast change of the fuel flow. The load signal here is a negative going pulse of 6 microseconds. At the output of this first monostable, there is a positive pulse of 200 microseconds. The negative going pulse of this output triggers a second monostable here, which delivers a positive pulse of 6 microseconds. Therefore, there is a delay of 200 microseconds between the transfer of the registers to the display and the reset of the counters. This circuit is used for the scrolling of the rightmost digit. There are two inputs. The first is the negative voltage, which is the output of the filter. Okay, so there is here a negative voltage which depends on the variation with time of the fuel flow. There is a negative threshold here. This voltage is minus 12 volts. So on that point, there is a voltage of minus 0.5, 0.6 volts, something like that. Therefore, when there is a change of the fuel flow, the output goes to minus 10 volts approximately. These two diodes are off. So therefore, the voltage across this resistor is at low level. Therefore, this signal indicates that we need to scroll the right digit of the display. And the direction is given by this second signal here, scrolling direction. For that purpose, this signal is connected to the output of the absolute value circuit, which is this signal. Okay, so this signal is at high level when there is an increase of the fuel flow. Therefore, when there is an increase of the fuel flow, this line is at high level. If there is a decrease, the voltage is negative. There is a low level on that line here. And the last circuit is this one. We have the coding wheels here on the top. We have here two 6-bit registers. Okay, so we can see that the output of the registers are connected to the drivers here. There is something different for the right digit, as we have seen. When the fuel flow is constant, the right digit has the same function than the other digits. Okay, so the fuel flow is displayed here. When there is a change of the fuel flow in one direction or another one, there is a scrolling of that display here. So this is done using this 4-bit multiplexer here. We can see that one 4-bit input here is connected to the register here. Okay, so it depends on the value of that signal, which is actually the scrolling display we have seen. When this line is at low level, the scrolling is enabled. In that case, these 4 lines here are connected to these 4 inputs here, and this 4-bit input is the output of this decimal counter, and the input of that counter is this simple astable here, which delivers the square wave. Okay, and the direction of counting depends on the scrolling direction we have seen. An important signal is this one, is the load signal, which permits to update the value. So we have something specific for the leftmost digit here, which is nothing or 1. So this is done using this D flip-flop. Okay, so the input of the flip-flop here is a carry of the last counter, okay, for the left digit. The load here permits to update the output of this flip-flop and to activate the 1 figure here or nothing. We have here the clock generator. It uses a crystal at 4.36 MHz approximately here. The signal is fed to this binary counter CD4040. The output Q1 here gives half this frequency, that is to say a frequency of 2.18 MHz approximately. 545 megahertz approximately. Oh, this is not megahertz but kilohertz. I think that this signal is not used. This circuit is not used. And we have here the main clock generator, which is used for the counters. So we can see on the bottom of the PCB, there is this small PCB, which seems to be a configuration PCB. This circuit is a clock divider. This frequency is divided by a number which depends on the input configuration here, which is given by this PCB. And at the output with the current configuration, there is a frequency of 4.53 kilohertz approximately. Okay, so the ratio is 962. So this value here is a scaling factor. The display of the result depends on this frequency here.